Tonight, we are going to follow one of the strangest consequences of living in an expanding universe. Not that distant galaxies are far away. Most people already know that. The strange part is that many of them are becoming permanently unreachable. Even if a spacecraft could travel at the speed of light, and even if it could continue that journey forever, there are destinations in the universe that it would never reach. Not because the journey is too long, because the universe itself is changing while the journey is underway. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. We will begin with what photographs have always shown us, and why those photographs, as beautiful as they are, carry a particular kind of deception built into their structure. We will move from there into the distances themselves, the actual separations between galaxies measured in units so large that the units themselves become hard to hold. Then we will look at what expansion means, not just as a word, but as a physical reality that changes the nature of distance in ways that have consequences no future technology can alter. We will spend time on the boundary that expansion creates, the horizon beyond which the universe becomes permanently unreachable, and we will look carefully at what it means that most of the galaxies we can see are already on the other side of that boundary. We will trace the structure of the universe at its largest scales, the web of filaments and the vast emptiness between them, and we will follow light backwards to the earliest moments it could travel freely, and think about what that record tells us and how long it will remain available to anything capable of reading it. And near the end, we will sit with the silence that answers one of the deepest questions humanity has asked about the universe, and think about what that silence actually means. None of this needs to be rushed. The distances are not going anywhere. The expansion will continue whether or not we follow it closely tonight. And the light arriving from 2 trillion galaxies has been traveling in some cases for nearly 14 billion years to reach us. So a few extra hours of careful attention seems like a reasonable way to receive it. If you are settling in for the night, you are in exactly the right place. Let the ideas come in gently. There is nothing here that requires urgency. The universe is old and patient, and tonight we are going to try to be the same. Let us begin. Chapter 1. What photographs lie? There is an image that many people have seen without knowing precisely what they were looking at. A small square of darkness, a patch of sky chosen because it appeared to contain nothing at all. No stars, no known galaxies, no visible features of any kind. Astronomers selected it for exactly that reason. They wanted to point a telescope at the emptiest piece of sky they could find and ask what nothing actually looked like up close. The telescope was the Hubble Space Telescope, then still relatively new to its work. The decision to dedicate 10 full days of observation time to a patch of sky that appeared to contain nothing was not universally welcomed. Observatory time is finite and carefully allocated, and pointing an instrument of that precision and cost at a region of apparently empty sky felt to some like a considerable gamble with a resource that had no shortage of competing demands. The scientists who proposed the observation believed the gamble was worth taking. They believed that a sky which looked empty to every previous instrument was not actually empty, and that the only honest way to test that belief was to look. In 1995, the data came back. That empty patch of sky contained approximately 3,000 galaxies, each one a structure containing hundreds of billions of stars. Each one a gravitational system so large that light, traveling at the only speed it knows, would take tens of thousands of years to cross from one edge to the other. 3,000 of them packed into a piece of sky, no wider than a grain of sand held at arm's length. The image was called the Hubble Deep Field, and it did something permanent to how astronomers and eventually the wider public understood the scale of what surrounds us. It was not a minor correction to an existing picture. It was a replacement of the picture entirely. But the image also carried a deception, not a deliberate one, not one introduced by the scientists who planned the observation or processed the data or released it to the public. A structural deception, one built into the nature of photography itself and impossible to remove regardless of the sophistication of the instrument doing the recording. A photograph is flat. It has width and height. It does not have depth in any form the eye can read naturally. When two objects appear close to each other in a photograph, the photograph cannot tell you whether they are genuinely near each other in three-dimensional space, or whether one lies vastly closer to the observer, and the apparent proximity is purely a consequence of the viewing angle. Two stars that appear side by side in a night sky image might be separated by a few light years, or they might be separated by thousands of light years, with one simply falling along the same line of sight as the other from where the observer happens to be standing. The photograph cannot distinguish between those two situations. It compresses depth into nothing, and in doing so, it creates a kind of false neighborhood, a sense of adjacency that has no physical meaning. In the Hubble Deep Field, and in every deep field image taken since, this compression does something specific that rewards careful attention. The galaxies in the image exist at vastly different distances from us. Some are relatively nearby in cosmic terms, perhaps a few 100 million light years away. Others are billions of light years more distant, seen not as they are, but as they were when the universe was a small fraction of its current age, when the structures we associate with mature galaxies were still forming, still chaotic, still nothing like the organized spirals and ellipticals visible in the foreground. The image layers all of them into a single plane. The way pressing flowers between the pages of a book flattens their three-dimensional form into a dried impression that looks complete, but has surrendered one of its essential dimensions permanently. When you look at a deep field image and see what appears to be a crowded neighborhood of galaxies, you are not seeing a neighborhood. You are seeing a line of sight. Everything along that line of sight for billions of light years in every direction has been compressed into a single flat frame. Some of the galaxies that appear adjacent are indeed relatively close to one another in space, but many pairs that look as though they almost touch are separated by distances so large that crossing them at the speed of a commercial aircraft would require something in the range of 200 trillion years. The age of the universe is approximately 14 billion years. A gap between 2 points of light that look small enough to cover with a fingertip in a photograph would require more than 14,000 universe lifetimes to traverse at the speeds we currently achieve in atmospheric flight. Your eye reads them as close. They are not close. They have never been close. The photograph simply has no mechanism for showing you how far apart they truly are. There is a second layer to this flattening, and it is in some ways more disorienting than the first once you absorb it fully. The galaxies in a deep field image are not all being seen as they exist right now. Light travels at a finite speed, and that fact has consequences that reach into everything we think we know about the appearance of the universe. The light that reaches a telescope from a galaxy 2 billion light years away left that galaxy 2 billion years ago. The image the telescope records is not the galaxy as it currently exists. It is the galaxy as it was 2 billion years in the past. A galaxy 10 billion light years away is being seen as it was 10 billion years ago, when the universe was not yet 4 billion years old, when many of the features we associate with mature galaxies had not yet had the time to develop. A deep field image does not show you a snapshot of the universe as it currently appears across all of space simultaneously. It shows you a cross-section of cosmic history. The nearest galaxies in the frame represent the relatively recent past. The most distant represent the universe's earliest readable chapters. Everything in between occupies a different point on a timeline stretching back nearly to the beginning. The image arranges them as if they exist together in a single moment, because that is what a photograph does. It records the moment of arrival at the detector. It has no mechanism for distinguishing between light that has been traveling for 200 million years and light that has been traveling for 13 billion years. Both arrive in the same exposure. Both become part of the same flat frame. The result looks like a neighborhood. It is actually a record of time, stacked in depth, with the oldest material at the back and the most recent at the front. The way geological strata preserve different eras of a planet's history in layers of rock that accumulate over millions of years. Take that understanding and extend it to the full inventory of what we can observe. The observable universe contains roughly 2 trillion galaxies. That number does not yield easily to intuition, because intuition was not built for numbers at this scale. If you counted 1 galaxy per second, without stopping and without sleeping, the count would take approximately 63,000 years to complete. If someone had begun that count on the day the first anatomically modern human beings were walking the African savannas, they would still be counting today, with tens of thousands of years remaining before they reached the end of the list. And every single one of those 2 trillion galaxies is separated from its neighbors by distances that photographs have always and will always misrepresent, not through any failure of technology, but through the fundamental nature of what a photograph is and what it cannot do. The illusion photographs create is not only about size, it is about the relationship between the matter that is visible and the emptiness that surrounds it. Photographs show you what is there. They render invisible what is not there, and what is not there is almost everything. The universe, measured honestly by volume, is almost entirely empty space. The galaxies, enormous as each one is, occupy a vanishingly small fraction of the total volume available to them. The distances between them are not like the distances between cities on a map, where there is at least land between one place and the next. They are more like the distances between isolated points of light, suspended in a darkness so complete and so extended that no landmark exists anywhere along the path between them. When we look at images of cosmic structure and feel that we understand what we are seeing, we are in the grip of a very specific kind of illusion. The correction is not comfortable, but it is the necessary beginning. Photographs flatten what is deep, they contemporize what is historical, and they populate what is, by almost any honest measure, almost entirely empty. That emptiness is where we are going next. Chapter 2. The Scale of Empty. Begin with something concrete. The Milky Way, the galaxy we live inside, is approximately 100,000 light-years across. That means light, traveling at just under 300,000 kilometers per second, takes 100,000 years to cross it from one edge to the other. If you scaled the Milky Way down to the width of a standard dinner plate, roughly 25 centimeters across, the nearest large galaxy to our own, the Andromeda Galaxy, would sit approximately 15 feet away from you in the same room. That already sounds like a significant amount of empty space between two objects. 15 feet of nothing, scaled down from 2.5 million light-years of nothing. But here is what that analogy does not yet tell you. Andromeda is, by the standards of the universe at large, our immediate neighbor. It is as close as galaxies get. Most galaxies are not 15 feet apart on that scale. Most galaxies are separated by distances that, on the same scale where the Milky Way fits on a dinner plate, would place their nearest neighbours at the far end of a football field, or across a city block, or further still. 2.5 million light-years is the distance to Andromeda. It is the smallest intergalactic gap in our immediate region of the universe. And 2.5 million light-years, to be precise about what that number means, is approximately 23.5 million trillion kilometers. Written as a numeral, that number would require enough digits that reading it aloud at a steady pace would take a noticeable amount of time. It is a distance so far outside the range of anything human experience can calibrate against that analogies begin to struggle the moment you try to construct them. The dinner plate and the 15 feet across the room is one of the more successful attempts, and even it collapses the moment you try to extend it to feel what travelling that distance would actually involve. Consider what crossing 2.5 million light-years would require in practical terms. The fastest spacecraft humanity has ever launched is the Parker Solar Probe, which at its closest approach to the Sun reaches speeds of approximately 700,000 kilometers per hour. That is genuinely fast by any measure derived from human experience. At that speed, you could circle the Earth in under 4 minutes. You could travel from the Earth to the Moon in under 30 minutes. You could reach Mars at its closest approach in a matter of weeks. At that speed, crossing the distance to Andromeda would take approximately 3.5 billion years. The Earth itself is approximately 4.5 billion years old. A journey to our nearest large galactic neighbour at the fastest speed any human-made object has ever achieved would take a length of time comparable to the current age of the planet beneath your feet. And Andromeda, to be clear again, is the close one. The distances between most galaxies in the observable universe are not measured in millions of light-years. They are measured in tens of millions, in hundreds of millions, and in many cases in billions of light-years. The average separation between galaxies, taken across the observable universe as a whole, is something in the range of several million light-years. But that average is heavily influenced by the fact that galaxies cluster together in groups and filaments, with the space between those clusters being vastly emptier than the space within them. The voids, the regions of the universe that contain essentially no galaxies at all, can span hundreds of millions of light-years in diameter. They are not rare features. They are the dominant structure of the universe by volume. The galaxies and clusters and filaments that we tend to focus on, because they are where the light comes from, occupy a relatively thin web of matter surrounding enormous bubbles of near-total emptiness. To understand what that emptiness actually means at a physical level, it helps to think about density. The average density of matter in the universe is extraordinarily low. If you took all of the matter in the observable universe, all of the stars and planets and gas and dust and everything else that is made of ordinary atoms, and spread it evenly throughout the volume of the observable universe, you would end up with roughly 1 hydrogen atom per cubic meter of space. 1 atom per cubic meter. The air you are breathing right now contains approximately 10 to the power of 25 atoms per cubic meter, a number so large it is essentially incomprehensible. The average density of the observable universe is 25 orders of magnitude lower than the air in a quiet room on a calm night. The universe is not like a room with some furniture in it. It is like a room in which the furniture has been replaced with a single atom, and the room itself is a cube roughly a meter on each side, and those rooms stretch in every direction for distances that make the word vast feel completely inadequate. Within that extraordinary emptiness, matter has organized itself into structures under the influence of gravity. The largest of those structures are the galaxy clusters, gravitationally bound collections of anywhere from a few dozen to several thousand individual galaxies, held together by the combined gravitational pull of all their constituent stars, gas, dark matter, and everything else their combined mass produces. Our own local group, the cluster that contains the Milky Way and Andromeda, and a few dozen smaller galaxies, is a relatively modest example of this kind of structure. Larger clusters exist, containing thousands of galaxies and enormous quantities of hot intergalactic gas, all gravitationally bound into a single system that will remain intact essentially indefinitely on any timescale relevant to human thought. But even within a galaxy cluster, even within a gravitationally bound system where the galaxies are as close to one another as galaxies ever get, the space between individual galaxies is not small. The galaxies in a cluster are separated by distances of hundreds of thousands to millions of light years. They are close enough to interact gravitationally, close enough to occasionally merge with one another over billions of years, but they are not close in any sense that makes the space between them easy to conceptualize. A photon of light emitted from a star in one galaxy of a cluster, traveling at the speed of light toward the nearest galaxy in the same cluster, might travel for several 100,000 years before reaching its destination. For all of that journey, in every direction, there would be essentially nothing. No stars, no planets, no gas dense enough to interact with. Just space. Beyond the clusters, between the filaments and sheets of the cosmic web, the emptiness deepens further. The great voids of the universe, the largest known of which, spans something in the range of 300 million light years across, contain so little matter that a photon of light could travel through them for hundreds of millions of years without a significant chance of encountering anything at all. Not a galaxy, not a cluster, not even the diffuse intergalactic gas that fills the spaces within filaments. The voids are as close to true nothingness as the physical universe produces, and they are not small features tucked between more substantial structures. They are the dominant feature. They are what most of the universe, by volume, actually is. There is a particular quality to this kind of emptiness that differs from the emptiness we encounter in ordinary experience. When we say a room is empty, we mean there is no furniture in it, no people, no objects of the kind that rooms are usually designed to contain. But the room still has air. It has walls. It has a floor and a ceiling. It is empty of certain things while being full of others. When we say a cosmic void is empty, we mean something closer to genuinely nothing. No air, no walls, no floor, no reference points of any kind. A traveler inside a cosmic void who happened to look in every direction would see, if they were lucky, the faint glow of the cosmic web on the horizon of the void, perhaps 150 million light years away in every direction. In the intervening space, nothing. No star to navigate by. No landmark to measure progress against. No way to determine, except by the most precise instruments imaginable, whether you were moving at all. This is the universe that photographs do not show. Not because photographs are bad instruments, but because photographs record light, and light comes from matter, and in the cosmos, most of the volume contains no matter worth speaking of. The deep field images show us 2 trillion galaxies, and they are genuinely there, and they are genuinely wondrous, but they are small, and they are sparse, and they are surrounded on every side by distances that the images cannot represent, and that intuition was never designed to handle. The dinner plate across the room is a beginning. The football field is a continuation. The empty cube with one atom in it is closer to the truth. But the truth, fully inhabited, is still beyond what any analogy built from human-scale experience can quite reach. The numbers are correct. The emptiness they describe is real. What is needed is not a better analogy, but a willingness to sit with the inadequacy of every analogy and let the reality underneath it come into partial focus slowly. The way a very faint object in the night sky sometimes becomes visible only when you stop looking directly at it and let peripheral vision do what direct attention cannot. The space between galaxies is not a backdrop. It is not scenery. It is the dominant fact of the universe's physical structure, and everything that follows in this video is a consequence of it. Chapter 3: Space that expands. There is a distinction that matters enormously, and that is easy to state but takes some time to fully absorb. When we say the universe is expanding, we do not mean that the galaxies are moving through space the way a stone moves through air when thrown, traveling from one location to another across a fixed background. We mean something different and in some ways more unsettling. The space itself is expanding. The background is not fixed. The distance between 2 points in the universe is increasing, not because those points are moving relative to the space between them, but because the space between them is growing. New distance is being added, continuously, between every pair of points in the universe that are not held together by a force strong enough to resist the expansion. Gravity holds galaxies together. It holds galaxy clusters together. But between clusters, between the large gravitationally bound structures, space is stretching, and it has been stretching since very early in the universe's history. This was not always known. For most of human history, the universe was assumed to be static, unchanging in its large-scale structure, perhaps infinite in extent, but not dynamic in the way we now understand it to be. The first serious observational evidence that the universe might be expanding came in the 1920s, when astronomers examining the light from distant galaxies noticed something systematic and unexpected. The light from those galaxies was shifted toward the red end of the spectrum, not by a small amount, and not in a random distribution. Almost every galaxy examined showed this redshift, and the more distant the galaxy appeared to be, the larger the shift. This is the signature of recession. When a source of light moves away from an observer, the waves of light it emits are stretched, lengthened, shifted toward longer wavelengths, which in visible light means shifted toward red. The galaxies were not simply moving, they were receding, and the further away they were, the faster they appeared to be receding. The interpretation that fit this data was that the universe is expanding uniformly in all directions. From any point within it, all other sufficiently distant points appear to be moving away, and the relationship between distance and recession speed follows a consistent ratio described by what is now called the Hubble constant. The universe is not expanding from a center, like an explosion spreading outward from a point of origin. It is expanding everywhere simultaneously, the way the surface of a balloon expands when you inflate it, with every point on the surface moving away from every other point, not because any point is at the center, but because the surface itself is growing. That analogy, the balloon, is useful and widely used, and like all analogies, it has limits worth noting. The balloon has a center inside the balloon, but the surface of the balloon, which is the analogy for space itself, does not have a center. Every point on the surface is equivalent to every other point in the relevant sense. The expansion looks the same from any location. An observer in any galaxy, looking out at the universe around them, would see the same pattern of recession that we see from the Milky Way. The expansion has no preferred viewpoint, no origin in space, no edge toward which everything is moving. It simply is, everywhere, all at once, and it has been happening for as long as we have been able to trace the universe's history backward. Now consider what this means for the distances between galaxies. A galaxy that is currently 1 billion light-years away from us is not sitting still, while the light it emits travels toward us. During the time that light is traveling, the space between that galaxy and us is expanding. The galaxy is being carried further away, not by any motion of its own through space, but by the growth of the space between us. The light is moving toward us through expanding space, which means it has more distance to cover than it would if space were static. When astronomers say that a galaxy is 1 billion light-years away, they are typically referring to what is called the comoving distance, a measure that accounts for the expansion and places the galaxy in its current position rather than where it was when the light we are now receiving left it. The distinction between where a galaxy was when it emitted the light we are now seeing and where it is now is not trivial. For the most distant observable galaxies, the ones whose light left them when the universe was a small fraction of its current age, the difference is enormous. Some galaxies we observe appear to be approximately 13 billion light-years away in terms of how long their light has been traveling. But the actual current distance to those galaxies, accounting for the expansion that occurred while their light was in transit, is significantly larger, in some cases more than 45 billion light-years. The observable universe is approximately 93 billion light-years in diameter, even though the universe is only approximately 14 billion years old, because the space has been expanding throughout the entire time the light has been traveling. This is not a contradiction. It does not violate the rule that nothing travels through space faster than light. The galaxies are not moving through space faster than light. The space between us and them is simply growing, and the growth of space is not subject to the same speed limit as the movement of objects through space. Space can expand at any rate. It can and does, in the most distant reaches of the observable universe, expand in a way that carries galaxies away from us faster than light could close the gap. Not because anything is moving too fast, but because the road between us and those galaxies is lengthening at a rate that exceeds the speed at which anything can travel along it. This brings us to a concept that will become central to much of what follows: the cosmic event horizon. The event horizon is the boundary beyond which the expansion of space is occurring fast enough that any signal we send today will never reach its destination. A photon of light emitted from Earth right now, aimed at a galaxy beyond the cosmic event horizon, will travel for billions of years and never close the gap. The space between the photon and the target galaxy will grow faster than the photon can move through it. The photon will travel forever and arrive nowhere. The galaxy it was aimed at will recede beyond any possibility of contact. The current distance to the cosmic event horizon is approximately 16 billion light-years. Any galaxy currently further than that from us is, in a physically meaningful sense, permanently unreachable. Not just difficult to reach, not just impractical to reach with current technology. Permanently unreachable in a way that no advancement in propulsion or engineering can address, because the barrier is not a technological one. It is a consequence of how space itself behaves, and it deepens with time. As the universe continues to expand, the event horizon does not stay in place. More galaxies cross it with every passing era. More of the observable universe becomes part of the unreachable universe. The window of what is physically accessible is not holding steady. It is closing. It is worth pausing here to distinguish between two different kinds of horizon that the expanding universe produces. One is the particle horizon, which is the boundary of the observable universe, the furthest distance from which any light has had time to reach us since the beginning of the universe. Everything within the particle horizon is observable in principle. Everything beyond it is not observable, because there has not been enough time for light from those regions to reach us. The particle horizon is large, approximately 45 billion light-years in radius, and it grows with time as the universe ages and light from more distant regions has more time to arrive. The other is the cosmic event horizon, the boundary beyond which signals sent now will never arrive. The event horizon is smaller than the particle horizon, currently approximately 16 billion light-years in radius, and unlike the particle horizon, it represents a permanent physical limit, rather than simply a limit of current observability. Galaxies within the particle horizon, but beyond the event horizon, can be seen, because light they emitted in the past has already reached us, but they cannot be reached, and nothing we send toward them will ever arrive. The expansion of space is not uniform in its rate across cosmic history. For the first several billion years after the beginning, the universe was expanding, but the expansion was slowing, pulled back by the collective gravity of all the matter within it. At that time, the event horizon was further away. More galaxies were on the reachable side of the boundary, and the future of intergalactic travel, while still extraordinarily difficult, was not structurally foreclosed in quite the way it is now. Then, approximately 5 billion years ago, something changed. The expansion stopped decelerating and began to accelerate. The rate of growth of space started to increase rather than decrease, pushed by something that has been named dark energy, a property of space itself, whose ultimate nature remains one of the genuinely open questions in physics. The acceleration of expansion has consequences that compound with time. As the expansion rate increases, the event horizon moves closer in relative terms. More galaxies are carried past it, and the fraction of the observable universe that is also within the reachable universe shrinks. The universe is becoming, in a very specific and measurable sense, more isolated with every passing billion years. Not more isolated in the sense that anything is being taken away from us suddenly. The Milky Way and its local group of galaxies are gravitationally bound and will remain so. The expansion does not affect structures held together by gravity, but the space between our local group and every other cluster, every other gravitationally bound island in the cosmic sea, is growing and will continue to grow, and will eventually grow to the point where the light from other clusters can no longer reach us at all. That era is far in the future, on timescales relevant to human life, or even to the life of our sun. The expansion is not something that changes daily experience in any way, but it is happening now, and it has been happening since long before the Earth formed, and it will continue long after the last stars in the last galaxies have burned out. The universe is not static. It never has been. And the direction it is moving in is not toward greater density or greater connection. It is toward greater separation, greater emptiness, and ultimately toward a kind of isolation so complete that the universe we currently observe, with its 2 trillion galaxies and its cosmic web and its faint background radiation, will be undetectable from within the last gravitationally bound islands that remain. The expansion of space is not just a cosmological fact. It is the context within which everything else about the distance between galaxies must be understood. The distances are not fixed. They are growing, and they are growing in a direction that makes the universe not just currently empty, but increasingly, permanently, irreversibly more so. Chapter 4. The Horizon We Cannot Cross. There is a number worth holding carefully. Roughly 94% of the galaxies in the observable universe are already beyond the cosmic event horizon, not approaching it, not near it, already past it, already on the other side of the boundary beyond which no signal sent today will ever arrive, already in a region of space that is, in the most complete physical sense available to us, permanently beyond contact. This is not a prediction about the distant future. It is a description of the present. The overwhelming majority of what we can see when we look at the universe is something we can never reach, never visit, never communicate with, and never influence in any way. The light arrives. Nothing else ever will. To understand why this fraction is so large, it helps to think carefully about what the observable universe actually contains and how it is distributed. The observable universe is a sphere approximately 93 billion light-years in diameter, centered on us, bounded by the particle horizon at a distance of roughly 45 billion light-years in every direction. Within that sphere, matter is not distributed uniformly. It is concentrated in the cosmic web of filaments and clusters, with vast empty voids between them, and the overall structure has been shaped by the expansion of space acting on the initial distribution of matter from the very beginning. The event horizon sits at approximately 16 billion light-years. Everything between 16 billion light-years and 45 billion light-years, a shell of enormous volume, contains galaxies we can observe but not reach. Given that volume scales with the cube of the radius, the fraction of observable volume that lies beyond the event horizon is very large. The 94% figure reflects the fact that most of the volume of the observable universe and most of the galaxies within that volume lie in the unreachable shell. Think about what that means for a moment without rushing past it. Every deep field image ever taken, every catalogue of distant galaxies ever compiled, every measurement of redshift and distance and structure that astronomers have accumulated over more than a century of careful observation, contains within it an enormous inventory of things that are permanently beyond reach. Not beyond reach in the way that a distant mountain is beyond reach for someone who cannot travel. Beyond reach in the way that yesterday is beyond reach. Not a practical barrier, a physical one. A feature of how space and time are structured that does not yield to any application of energy or intelligence or ambition. The galaxies beyond the event horizon are not hidden. We can see them perfectly well. The light they emitted billions of years ago is still arriving, still carrying information about their structure and their distance and their motion. In some cases, we have detailed images of these galaxies, their spiral arms or elliptical forms clearly resolved, their colors and spectra measured with precision. We know a great deal about many galaxies that we can never reach. The knowledge is real. The barrier is also real, and the two coexist in a way that has no clean parallel in ordinary human experience. There is something specific that happens to a galaxy once it crosses the event horizon that is worth understanding precisely. It does not disappear. It does not go dark suddenly. The light it has already emitted continues to travel toward us and will continue to arrive for a very long time. What changes is the future. Any light emitted by that galaxy from the moment it crosses the horizon onward will never reach us. The galaxy will continue to exist, to evolve, to form stars, and perhaps harbor whatever complexity physics allows. But every photon it emits from that point forward is emitted into a region of space from which it can never close the growing gap between us. The connection is not severed suddenly and dramatically. It thins over a very long time, with the last light we ever receive from a given galaxy arriving redshifted to the point of being undetectable, stretched by the expansion until its wavelength is longer than any instrument could measure. then silence. Not the silence of something ending abruptly, but the silence of something fading so gradually that there is no single moment you could identify as the last. This gradual fading matters because it means the event horizon is not an experience in the way a physical boundary would be. It is not a wall. It is not a place where one side looks different from the other. A traveler crossing the event horizon would not notice anything at the moment of crossing. The boundary exists only in the mathematics of how space expands over time, and its consequences are only apparent in retrospect when you calculate what signals can and cannot eventually arrive at a particular location. The horizon is a feature of the future light cone of the universe, not a feature of space as it appears locally at any given moment. What this means, in practical terms, is that the foreclosure of contact with most of the universe is not something that happened at a single identifiable moment. It has been happening gradually, continuously, since the acceleration of expansion began approximately 5 billion years ago. Galaxies have been crossing the event horizon one by one, at a rate that has been increasing as the expansion accelerates, and they will continue to do so for as long as the expansion continues to accelerate. The process is ongoing and irreversible. There is no mechanism within known physics by which a galaxy that has crossed the event horizon can cross back. The direction of travel is one way only. It is also worth being precise about what the event horizon is not. It is not the edge of the universe. The universe, as best we can determine, has no edge in the conventional sense. It may be infinite in extent, containing an infinite number of galaxies beyond the particle horizon that we will never observe simply because their light has not had time to reach us. The event horizon is not a boundary of the universe itself. It is a boundary of reachability from our specific location at this specific time, given the current rate of expansion and the way that rate is changing. A different location in the universe would have a different event horizon, centered on itself, enclosing a different set of galaxies. The horizon is not a feature of the universe from outside. It is a feature of a perspective from within. This distinction matters because it prevents a common misunderstanding. The universe beyond the event horizon is not somehow less real or less present than the universe inside it. The galaxies out there are not diminished by being unreachable. They are full, complete, active galaxies doing everything galaxies do, forming stars, hosting whatever complexity their physics allows, existing fully in every physical sense. The unreachability is entirely a feature of the geometry of space between them and us, not a feature of them. They are there. We simply cannot get there, and nothing we send can either. The 94% figure can feel, when you first encounter it, like a kind of loss, and in a sense it is. It describes a universe in which the vast majority of what exists is structurally inaccessible, in which the observable and the reachable are two very different things, and in which the gap between them is growing. Every century that passes, more galaxies cross the horizon. Every billion years, the fraction of the observable universe that is also within the reachable universe decreases. The universe is not just expanding. It is, from the perspective of any point within it, becoming more enclosed. The island of reachable space is not growing with the overall expansion. It is, in relative terms, shrinking. But there is another way to hold this, one that requires no adjustment of the facts, but simply a different angle of attention. The 94% that is unreachable is not lost to us in the sense of being unknowable. The light still comes. The information still arrives. We can study those galaxies in detail, measure their properties, trace their history, map their positions in the three-dimensional structure of the cosmic web. The foreclosure of physical access does not foreclose knowledge. It forecloses only the kind of knowledge that requires presence, the kind that requires sending something or going somewhere, and that kind of knowledge, when the destination is a galaxy tens of billions of light years away, was never a realistic near-term prospect regardless of the event horizon. What the event horizon does, most precisely, is settle a question permanently. It removes from the category of things that are merely very difficult and places them in the category of things that are physically impossible. That is a different kind of boundary from the ones we normally encounter. Most limits we face are practical limits, limits of energy or time or technology that might in principle be overcome given sufficient resources. The cosmic event horizon is not that kind of limit. It is a limit written into the structure of space-time by the rate at which space expands and the rate at which that rate is increasing. No amount of energy closes it. No technology crosses it. No future civilization, however advanced, sends a successful signal to a galaxy that has crossed the event horizon and receives a reply. The universe, then, contains within it a permanent and growing set of things that are visible but unreachable, knowable at a distance but never approachable, present in the light that arrives, but absent from any possible future in which anything physical travels between us and them. That is a remarkable feature of the cosmos we inhabit. It is not hidden or obscure. It follows directly from the geometry of expansion and the way the expansion rate has been changing for the past 5 billion years. It is simply not the kind of fact that everyday experience prepares us to hold. The horizon exists. It is real. And everything beyond it is, in the most literal physical sense, already gone from the reachable universe. We are seeing its light. We will continue to see its light for a very long time. But the connection it represents is a one-way connection, a record arriving from a relationship that can never be reciprocal. The universe is showing us something it will not let us touch. Chapter 5. The Cosmic Web. If you could step outside the universe and look at it from a distance large enough to take in its full structure, the first thing you would notice is not the galaxies. The galaxies, individually, are too small to resolve at that scale. What you would see is the pattern they form together, the large-scale arrangement of matter that has developed over 14 billion years under the influence of gravity acting on the slight unevenness that was present in the very earliest moments of cosmic history. What you would see is something that looks, with remarkable consistency, like a web. The cosmic web is the name astronomers give to the large-scale structure of the universe, and it is one of the more striking discoveries of the past several decades of observational cosmology. It is not a metaphor or a loose comparison. The universe, at the largest scales we can map, genuinely organizes itself into a network of filaments and sheets and nodes that bears a strong structural resemblance to biological neural networks, to the growth patterns of certain fungi, to the branching of river deltas, and to the strands of a spider's web covered in dew on a still morning. The resemblance is not coincidental in the sense of meaning anything mystical or designed. It is the natural consequence of gravity acting on a nearly uniform but slightly uneven distribution of matter over very long periods of time. In the very early universe, the distribution of matter was almost perfectly uniform. Almost, but not quite. There were tiny variations in density, fluctuations at the quantum level that were stretched to cosmic scales during a period of extremely rapid expansion in the universe's first fraction of a second. These fluctuations were small, variations in density of roughly 1 part in 100,000. But gravity is patient, and over billions of years those tiny variations were amplified. Regions that were slightly denser than average attracted more matter, which made them denser still, which attracted more matter. Regions that were slightly less dense lost matter to their denser neighbors, becoming emptier over time. The process is self-reinforcing, and it operates on every scale simultaneously, which is why the structure that emerges has the same basic character at many different scales. A web-like pattern of denser and emptier regions, nested within larger, denser and emptier regions. The result, after 14 billion years of this process, is a universe structured as follows. At the larger scales, there are enormous voids, regions hundreds of millions of light-years across, that contain essentially no galaxies. These voids are not uniform. They have subtle internal structure, and they are bounded on their surfaces by sheets and filaments of matter. The sheets are flattened concentrations of galaxies arranged in rough planes. The filaments are elongated concentrations, strings of galaxies and intergalactic gas stretching for hundreds of millions of light-years. Where filaments intersect, where the web's threads cross, the density is highest. These intersection points are where the most massive galaxy clusters form. Gravitationally bound concentrations of hundreds or thousands of galaxies embedded in enormous halos of dark matter and hot intergalactic gas. The largest known structures in the universe are features of this web. The Hercules Corona Borealis Great Wall, identified in the early 21st century, is a concentration of galaxies spanning approximately 10 billion light-years, making it one of the largest known structures in the observable universe. The Sloan Great Wall, identified somewhat earlier, spans roughly 1.5 billion light-years. These are not walls in any physical sense, not solid structures with surfaces you could approach and touch. They are statistical overdensities, regions where the probability of finding a galaxy is higher than average, arranged in roughly planar or filamentary configurations that trace the skeleton of the cosmic web at the very largest scales. The voids between these structures are equally remarkable and in some ways more instructive. The Boötes void, one of the better studied large voids, spans approximately 330 million light-years. Inside it, there are almost no galaxies. A few have been found near its interior, but they are rare exceptions in a space that is, by the standards of the universe everywhere else, essentially empty. If our Milky Way were located inside the Boötes void, the night sky would look very different from how it looks now. The nearest galaxies would be hundreds of millions of light-years away instead of a few million. The entire visible structure of the cosmic web that we can currently map would be concentrated in a shell far out at the edge of the void. The night sky, even with the most powerful telescopes ever built, would appear far more sparsely populated with distant light than it does from our current location in a relatively well-populated region of the cosmic web. The voids are not completely empty. They contain a diffuse intergalactic medium, gas so thin that it is nearly impossible to detect by conventional means. They may contain dark matter distributed at densities far below those found in filaments and clusters. They may contain small, faint dwarf galaxies that have so far escaped detection. But in any meaningful comparison to the rest of the universe, they are as close to nothing as the physical universe produces. They are the universe's baseline state, the default condition toward which everything tends when gravity has not gathered enough matter together to produce something denser. And they are, by volume, the dominant feature of the universe. The filaments and sheets and clusters that we tend to focus on, because they contain the visible matter, occupy a relatively thin scaffolding surrounding enormous volumes of near-total emptiness. Understanding the cosmic web also requires understanding how it formed over time, because the structure we observe today is not static and has not always looked the way it does now. In the early universe, when the background radiation we now detect as the cosmic microwave background was released, the density variations were still small. The web was only beginning to form. Over the first few billion years, the filaments grew more pronounced, the voids emptied more completely, and the galaxy clusters at the nodes of the web became more massive as they drew in matter from their surroundings along the filaments feeding them. The web has been growing more pronounced over time, its contrast sharpening, its voids deepening, its nodes growing heavier. Dark matter plays an essential role in this process that is worth pausing on. The ordinary matter we can see, the stars and gas and dust, accounts for only a small fraction of the total matter in the universe. The majority of the universe's matter content is dark matter, a form of matter that does not emit, absorb, or scatter light, but does have gravitational effects that are clearly detectable in how galaxies move and how large-scale structure forms. The cosmic web we observe in the distribution of galaxies is actually tracing a much more massive underlying web of dark matter. The galaxies form and cluster preferentially in the regions where dark matter has already concentrated, because the dark matter's gravitational influence is what draws the ordinary matter into those regions in the first place. This dark matter web, invisible to direct observation, is the skeleton on which the visible universe is built. The filaments of galaxies trace dark matter filaments. The clusters at the web's nodes sit within enormous halos of dark matter. Even the voids, largely empty of ordinary matter, are not completely empty of dark matter, though dark matter densities in voids are far lower than those in filaments. The universe's large-scale structure is, in a fundamental sense, the story of dark matter's gravitational influence on everything else, with ordinary matter following along, pooling in the gravitational wells that dark matter has prepared, forming stars and galaxies and all the complex structure that light eventually reveals. When astronomers map the cosmic web, they do so primarily by measuring the positions of galaxies and tracing the patterns they form. This is a substantial technical undertaking. The largest galaxy surveys ever conducted have mapped the positions of hundreds of millions of galaxies across large fractions of the observable universe, building a three-dimensional picture of the web structure that has become one of the foundational datasets of modern cosmology. These maps reveal the filaments and voids and clusters with striking clarity, and they match the predictions of theoretical models built on the assumption that the universe started with small density fluctuations and evolved under gravity and dark energy in the way the standard model of cosmology describes. The match between the theoretical predictions and the observed structure is one of the stronger pieces of evidence that we understand, at least in broad outline, how the universe works. The web is not an accident in the sense of being unexplained. It is the expected output of well-understood physics operating over well-understood timescales on well-established initial conditions. That it looks like a web, that it has this particular aesthetic quality that strikes human observers as simultaneously familiar and alien, is a consequence of those physics, not a separate fact to be explained. What the cosmic web tells us, finally, about the distance between galaxies is this: the emptiness between galaxies is not random. It is structured. It is the result of a specific physical process operating over the full history of the universe. The voids are where matter was pulled away from. The filaments are where matter accumulated. The clusters are where the accumulated matter concentrated most densely. Every feature of the distance and emptiness we have been exploring in this video has the cosmic web as its organizing context. The galaxies are not scattered uniformly through space with uniform gaps between them. They are gathered into a pattern, and the pattern has enormous empty regions built into it as a necessary consequence of the same gravity that built the concentrations. The universe is not uniformly empty. It is specifically empty in specific places and specifically full in others, and the arrangement of empty and full follows a logic that 14 billion years of physics has written into the structure of space. We live in one of the full places. Most of the universe, by volume, is one of the empty ones. Chapter 6. Light as Ancient Record. Every piece of information we have ever gathered about the universe beyond our immediate neighborhood has arrived in the form of light. Not light only in the narrow sense of visible wavelengths that the human eye can detect, but light in the broader sense of electromagnetic radiation, which includes radio waves and microwaves and infrared and ultraviolet and X-rays and gamma rays, all of them traveling at the same speed through the vacuum of space, all of them carrying encoded within their properties information about the source that emitted them and everything they passed through on the way. Astronomy is, at its foundation, the science of reading light. It is the science of decoding messages that were sent before the message readers existed, by sources that in many cases no longer exist in the form they had when the message was sent, across distances so large that the sending and the receiving are separated by intervals of time that dwarf the entire history of life on Earth. This is not a poetic description. It is a precise account of what astronomical observation actually involves. When a telescope collects light from a galaxy 10 billion light-years away, it is collecting photons that left their source 10 billion years ago. The detector records the arrival of something that has been traveling since a time when the universe was less than 4 billion years old, when the Milky Way was still assembling itself from infalling gas and early stellar generations, when there was no solar system, no Earth, no chemistry that would eventually produce anything capable of building a telescope. The photon arrives and is counted, and from it astronomers extract information. The wavelength, which tells them about the motion of the source and the expansion of the space the photon crossed. The intensity, which tells them about the luminosity of the source. The spectrum, which tells them about the chemical composition of the source and its temperature and density. All of that information was encoded in the photon 10 billion years ago and has been carried faithfully through the expanding universe until this moment. Light as a record keeper is not perfect. It is subject to absorption and scattering by material it passes through. It is redshifted by the expansion of space, its wavelength stretched so that light emitted in the ultraviolet can arrive in the infrared after a sufficiently long journey through the expanding universe. It can be gravitationally lensed, bent by the gravitational fields of massive objects it passes near, which distorts the apparent position and shape of the source. And it carries information only about what was happening at the source at the moment of emission, not about what has happened there since. The galaxy we see as it was 10 billion years ago may have merged with another galaxy 5 billion years ago and look entirely different today. The light record is a historical document, not a live feed. But within those limitations, light is the only record we have, and it is a remarkably rich one. The spectrum of light from a distant galaxy is like a fingerprint, carrying the signatures of specific chemical elements in the form of absorption and emission lines at particular wavelengths. These lines are the same in every galaxy, produced by the same physics everywhere in the universe, which means they can be identified even when they have been shifted to different wavelengths by the galaxy's recession. By measuring how much the lines have shifted from their rest wavelengths, astronomers can determine how fast the galaxy is receding and, combined with the relationship between recession speed and distance established by the expansion of space, how far away it is. The entire framework of extragalactic distance measurement rests on this technique, applied across billions of light years and hundreds of millions of observed galaxies. The most ancient light we can detect is the cosmic microwave background radiation. This is the light that was released approximately 380,000 years after the beginning of the universe, at the moment when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before this moment, the universe was a hot, dense plasma, opaque to light in the way that the interior of a star is opaque. Photons could not travel freely. They were constantly scattering off free electrons, bouncing around in a fog of charged particles. When the plasma cooled enough for neutral atoms to form, the fog lifted. Photons were suddenly free to travel, and they have been traveling ever since, in every direction, filling the universe with a bath of radiation that has been cooling and redshifting for approximately 13,800,000,000 years. Today, that radiation is detectable as microwaves, having been stretched by the expansion of space from the visible and near-infrared wavelengths it had when it was released to the much longer microwave wavelengths it has now. It arrives from every direction in the sky with almost perfect uniformity, a temperature of approximately 2.7 degrees above absolute zero. The tiny variations in this temperature, fluctuations at the level of roughly 1 part in 100,000, are the imprints of those original density variations in the early universe, the same variations that seeded the cosmic web. The cosmic microwave background is, in this sense, a photograph of the universe as it was 380,000 years after the beginning, a snapshot of the conditions that produced everything that followed, preserved in the form of light that has been traveling ever since and is arriving at our detectors right now. Reading the cosmic microwave background has been one of the most productive scientific endeavors of the past several decades. Satellites dedicated to mapping its temperature variations across the entire sky have produced data that constrains the fundamental parameters of cosmology with extraordinary precision. The total density of the universe, the fraction of that density contributed by ordinary matter and dark energy, the rate of expansion, the geometry of space on the larger scales, the entire standard model of cosmology, the framework within which we understand the universe's history and structure, is built in large part on the information encoded in that ancient light. It is the oldest message we have ever received, sent when the universe was less than 400,000 years old, and it tells us an enormous amount about where we came from. But there is a limit to how far back light can take us. Before the release of the cosmic microwave background, the universe was opaque. Light cannot carry information to us from those earliest moments, not electromagnetic light of any wavelength. The plasma was too dense, too hot, too thoroughly scattering for photons to travel freely. Whatever happened in the first 380,000 years of the universe's history is not recorded in the light we can detect. It is recorded in other things, in the abundances of the light elements produced in the first few minutes of nuclear reactions, in the large-scale structure of the universe that grew from those early density fluctuations, in the properties of the cosmic microwave background itself, which carries the imprint of what happened before it was released. But the direct light record stops at that wall. Before it, the universe was, from the perspective of photons, a closed room. This wall has a name, the surface of last scattering. It is not a physical surface in space. It is a surface in time, the moment when the universe became transparent, and we see it projected onto the sky in every direction as the cosmic microwave background. Everything we see when we look at the cosmic microwave background is coming from this surface, which was at the time approximately 42 million light-years away from any given point, but is now, accounting for the expansion of space since then, approximately 45 billion light-years away. The surface of last scattering is the back wall of the observable universe in the sense of the furthest surface from which light has reached us, and it is the oldest light we will ever be able to detect with any electromagnetic instrument. The light record between the surface of last scattering and the present day is not uniformly available. There is a period in the universe's history, sometimes called the Cosmic Dark Ages, stretching from the release of the cosmic microwave background at roughly 380,000 years after the beginning, to the formation of the first stars somewhere between 100 million and 200 million years later. During this period, the universe contained no sources of light. It was filled with neutral hydrogen gas, slowly cooling, slowly clumping under gravity, but not yet dense enough anywhere to ignite nuclear fusion. The universe was dark in the most literal sense. No stars, no galaxies, no light of any kind, except the fading glow of the cosmic microwave background and the gravitational processes that were beginning to build the structures that would eventually become the first galaxies. The end of the Dark Ages is marked by what astronomers call the epoch of reionization, when the first stars formed and began emitting ultraviolet radiation intense enough to ionize the neutral hydrogen gas around them. This reionization of the intergalactic medium was a gradual process, not a single event, spreading outward from the first stellar populations as more and more stars formed in more and more early galaxies. By approximately 1 billion years after the beginning, the reionization was largely complete, and the universe had taken on a character more recognizable as the cosmos we inhabit today, populated with galaxies emitting light across the electromagnetic spectrum into an intergalactic medium that was now ionized and transparent. Reading the light from the epoch of reionization is one of the frontiers of current observational astronomy. The James Webb Space Telescope, launched in late 2021 and operational from 2022 onward, was designed in part to observe the first galaxies and the earliest stages of cosmic structure formation at wavelengths that allow it to see through the cosmological redshift to sources at extreme distances. Its observations have already pushed the confirmed boundary of the observable galaxy population back to redshifts corresponding to the universe being only a few 100 million years old, providing direct light-based evidence of the earliest stages of galaxy formation that were previously accessible only indirectly. What all of this establishes is that the light arriving at our telescopes is not a uniform stream of current information. It is a layered archive of different cosmic epochs, with different wavelengths and different observational techniques accessing different chapters of the universe's history. The nearest galaxies tell us about the recent past. The most distant tell us about the universe's infancy. The cosmic microwave background tells us about the moment the universe became transparent, and the absence of detectable light before that moment tells us about a universe so different from the one we inhabit that it would be unrecognizable to direct observation. The record is rich, and it is still arriving. Every night that a telescope points at the sky, more of it comes in, from more sources at more distances, adding detail and depth to a picture that has been accumulating since the first human beings turned their attention upward and began to wonder what the lights above them actually were. We are still doing that. The instruments are better. The questions are more specific. But the act is the same. and the light obligingly continues to arrive, patient and faithful, carrying its ancient cargo across distances that have no good analogy in anything experienced at human scale. The record will not always be available. The expansion of space is redshifting the light from distant sources to longer and longer wavelengths, and eventually, far in the future, the most distant sources will be shifted beyond the reach of any conceivable detector. The cosmic microwave background will cool below any detectable threshold. The most remote galaxies will fade from observability entirely. The archive is not permanent. It is available now, in this era, and the window in which it can be read is finite. That finite window is the subject we turn to next. Chapter 7. The Privileged Era. There is a particular position in time that we occupy without having chosen it, and without, for most of human history, having understood what it meant. We live in what cosmologists sometimes refer to as the privileged era, a window in the universe's history during which the conditions necessary for observing the universe's full structure and history are simultaneously in place. The cosmic microwave background is still detectable. The most distant galaxies are still visible. The cosmic web is still mappable in its full extent. The expansion rate is measurable. The evidence of the beginning is still arriving. All of the information needed to reconstruct the universe's history from its first fraction of a second to the present day is, right now, available to any civilization sufficiently advanced to build the instruments to read it. That will not always be true. In fact, on cosmic timescales, it will not be true for very much longer. To understand why this era is privileged, it helps to think about what the universe will look like in the far future, and to work backward from that picture to appreciate what is present now that will eventually be absent. Consider a time approximately 1 trillion years from now, long after the last stars in the Milky Way have exhausted their fuel and gone dark, long after the sun has expanded into a red giant and eventually collapsed into a cooling white dwarf, long after every process associated with active stellar life in our galaxy has concluded. At that point, the universe will be unimaginably different from what it is today. The accelerating expansion of space will have carried every galaxy cluster beyond our local group so far away that their light will no longer reach us. Not dim to the point of being difficult to detect. Gone entirely. Redshifted beyond any wavelength that physics permits to be detected. Carried past the event horizon and into permanent silence. An observer in the Milky Way at that future time, assuming anything capable of observation still existed, would look out at a universe that appeared to contain only the galaxies of the local group. The Milky Way, Andromeda, the Magellanic Clouds, and a few dozen smaller companions, all merge by then into a single large elliptical galaxy, sometimes called Milkomeda, surrounded by an apparently empty universe with no visible neighbors and no detectable background radiation. The cosmic microwave background will have cooled to a temperature so close to absolute zero that no instrument built from matter could detect it. From inside that future universe, an observer would have essentially no way of knowing that the cosmos had ever been anything other than a single island galaxy surrounded by infinite darkness. The evidence of the Big Bang would be gone. The evidence of the cosmic web would be gone. The recession of distant galaxies, which was the original observational clue that the universe was expanding, would be undetectable because there would be no distant galaxies to observe. The entire framework of modern cosmology, every conclusion we have drawn about the universe's origin, age, structure, and fate, rests on observations that will simply not be available to any observer who arrives too late. We have not arrived too late. We are here now, in the window, when all of it is still visible, still measurable, still capable of being assembled into a coherent picture of cosmic history. That is what makes this era privileged. Not privileged in the sense of being specially arranged for our benefit, not privileged in any teleological sense at all. Privileged in the precise physical sense that the information needed to understand the universe's full history is currently present in the observable universe in a form that can in principle be detected and interpreted, and that this condition is temporary. The cosmic microwave background is the most striking example of evidence that is currently available but will not always be. As the universe expands, the background radiation cools. It is currently at approximately 2.7 degrees above absolute zero. In 1 trillion years, it will be 1 trillion times cooler than that, a temperature so close to absolute zero that the individual photons will have wavelengths longer than the observable universe itself, making them undetectable by any conceivable physical means. The background radiation does not disappear in any absolute sense. The photons continue to exist, but they become physically unreadable, stretched beyond the point where any interaction with matter is possible. The oldest and most fundamental piece of evidence for the Big Bang fades into physical inaccessibility. The recession of galaxies, the other foundational piece of evidence for the expanding universe, will also become unreadable as galaxies cross the event horizon and their light ceases to arrive. Right now, we can measure the redshifts of galaxies across a substantial fraction of the observable universe and trace the history of the expansion rate over billions of years. We can see galaxies at many different distances and therefore at many different points in cosmic history, and by comparing them, we can reconstruct how the expansion rate has changed over time. This reconstruction is how we know that the expansion began decelerating and then started accelerating approximately 5 billion years ago. It is how we know about dark energy. It is how we have been able to build the standard model of cosmology that describes the universe's history with the precision it currently achieves. A future observer, with access only to the local group and nothing beyond it, would have no way to make these measurements. There would be nothing to measure the recession of. There would be no distant galaxies to compare to nearby ones. The very observations that revealed the expanding universe would be unavailable. An intelligent civilization arising in that future era, building its telescopes and pointing them at the sky with great care and sophistication, would conclude that they lived in a static universe, a single large galaxy surrounded by empty space, with no evidence of expansion, no detectable background radiation, no indication that any of what we know about cosmic history was ever true. They would be wrong, but they would have no way of knowing it. The evidence would simply not be there. This thought experiment is not merely illustrative. It points to something genuine and important about the relationship between observation and knowledge. What we know about the universe depends entirely on what evidence is available to us. The privileged era argument suggests that we happen to exist at a time when an unusually large amount of evidence is available, when the universe's history is still readable in the light that surrounds us, and that this condition is a consequence of where we fall on the cosmic timeline, rather than anything special about our location in space. We are not at the center of the universe, but we may be, in a meaningful sense, near the center of the era during which the universe is most fully observable. The beginning of the privileged era can be traced to the moment the universe became transparent, the release of the cosmic microwave background approximately 380,000 years after the beginning. Before that moment, the universe was opaque, and no light-based record of its earlier state could propagate. After that moment, the light record began accumulating, and it has been accumulating ever since. The end of the privileged era, as described above, comes with the accelerating expansion carrying all evidence of the universe's large-scale structure beyond detectability. Between those two endpoints lies a window, and we are currently somewhere within it. Where within it is an interesting question. The universe is currently approximately 13.8 billion years old. The era during which the cosmic web is fully mappable and the cosmic microwave background is detectable probably extends for another several tens of billions of years, perhaps 100 billion years, before the combination of stellar burnout and cosmic expansion has progressed far enough to make the full picture unreadable. On that timescale, we are still in the relatively early portion of the privileged era, not at its beginning, but not near its end. There is still a great deal of the window remaining, but the window is finite, and the direction of travel is toward closure. The privileged era has another dimension that is worth exploring: the era of stars. Stars are not permanent features of the universe. They form from gas clouds when gravity compresses gas to the point of nuclear ignition, and they burn until they exhaust the fuel available for fusion, and then they die in various ways depending on their mass. The universe currently has abundant supplies of gas from which new stars can form, and star formation is ongoing in galaxies across the observable universe. But star formation will not continue indefinitely. The raw material, the hydrogen and helium gas that stars consume, is gradually being converted into heavier elements and locked away in stellar remnants. The rate of star formation across the universe has already been declining for approximately 10 billion years, having peaked when the universe was roughly 3 to 4 billion years old. At current rates of decline, star formation will continue at a reduced but non-zero level for tens of billions of years before the available gas supply becomes too depleted to sustain it. After that, the universe will enter a long era, sometimes called the degenerate era, in which the only surviving stellar objects are the dim remnants of dead stars. White dwarfs cooling slowly over trillions of years, neutron stars, and black holes. The brief, bright era of active star formation, the era we currently inhabit, is a relatively narrow window in the universe's total history, bracketed on one side by the formation of the first stars, and on the other by the exhaustion of the star-forming gas supply. We exist within that window. The Sun is a middle-aged star in a galaxy that is still actively forming new stars. The sky contains stars of every age, from ancient red dwarfs that formed in the Milky Way's earliest days, to young blue giants that formed within the last few million years. The universe is, right now, at or near the peak of its complexity, in terms of the variety and activity of stellar processes occurring simultaneously. That peak will not last. The trend is toward fewer new stars, toward an older and dimmer stellar population, toward a sky that grows quieter over billions of years as the bright young stars die and are not replaced at the same rate. The privileged era, then, is not just about observability in the technical sense of what instruments can detect. It is about the state of the universe itself, the era in which stars are burning, in which galaxies are active and evolving, in which the cosmic web is still growing more pronounced, in which the large-scale structure of the universe is at or near its maximum complexity and visibility. All of these conditions are temporary. All of them are products of where the universe currently is in its history, and all of them are conditions under which something like life and observation and knowledge building are possible. There is something worth sitting with quietly at the end of this chapter. The privileged era is not a resource that can be managed or extended. It is not something that careful planning or technological advancement can prolong. It is a feature of the universe's timeline, determined by the physics of expansion and stellar evolution and the cooling of radiation. We exist within it, not because of anything we did, but because the timescale on which stars form and planets form and life evolves happen to fall within the window when the universe is bright enough and structured enough to observe. Had the timescale of biological evolution been 10 times longer, we might have arrived after the peak of star formation had passed. Had it been 100 times longer, we might have arrived in an era when the cosmic microwave background was already undetectable and the recession of galaxies already invisible. We arrived when we did. The window is open. The light is coming in from 2 trillion galaxies and from the oldest surface in the observable universe and from every point in between. The cosmic web is mappable. The expansion rate is measurable. The history of the universe from its first moments to the present day is encoded in the radiation that surrounds us and is available to any mind patient enough and well-equipped enough to read it. That availability is not permanent. It is a gift of timing, offered by a universe that does not give gifts, that has no intentions and no preferences, but that happens in this era, in this window, to have arranged itself in a way that makes understanding possible. The arrangement will change, the window will close, but right now, tonight, the light is still arriving. Chapter 8. Silence and the Fermi Question. There is a question that has been asked in various forms for as long as human beings have understood that the universe contains more than one solar system, and that was given its most memorable modern formulation by the physicist Enrico Fermi during a casual lunchtime conversation in 1950. The question is simple enough to state in a single sentence. If the universe is as large and as old as we now know it to be, and if the conditions that produced life on Earth are not extraordinarily rare, then where is everybody? Where are the signals, the artifacts, the evidence of the countless civilizations that should, by any straightforward probabilistic reasoning, have arisen across billions of years in billions of galaxies? The universe is vast and ancient. Life arose here. Why does the sky appear to be silent? This question, known as the Fermi paradox, has accumulated a substantial literature of proposed answers over the decades since Fermi posed it. Some of those answers invoke the rarity of the conditions for life. Perhaps the emergence of complex life requires a combination of circumstances so improbable that even in a universe of 2 trillion galaxies, it has happened only once or only a handful of times. Perhaps the development of technological intelligence from whatever primitive life forms might exist elsewhere is itself an improbable step, a filter so difficult to pass that the vast majority of life-bearing worlds never produce anything capable of building a radio transmitter. Perhaps civilizations that do reach technological sophistication reliably destroy themselves before they can make themselves detectable across interstellar distances, so that the universe is populated with the ruins of civilizations that briefly flickered into existence and then went dark. Other answers invoke the distances themselves, and these are the ones that connect most directly to everything we have been exploring in this video. Even if the universe is full of civilizations, the distances between them may simply be too large for any signal to bridge on any timescale relevant to a civilization's existence. A civilization that has been broadcasting radio waves for 100 years, as humanity has sent signals that have traveled 100 light years in every direction. That is a sphere 100 light years in radius. The Milky Way is 100,000 light years across. the signals have reached a tiny fraction of even our own galaxy, a bubble so small relative to the galaxy's volume that the probability of it having intersected another civilization's detection capability is extremely low, even if the galaxy is densely populated with technological species. And that is within our own galaxy. The distances between galaxies make intergalactic communication a prospect so demanding of time that any exchange of information would require millions of years at minimum, longer than any civilization in the historical record has existed by many orders of magnitude. The silence in this framing is not a paradox at all. It is the expected consequence of the distances we have been describing throughout this video. If signals travel at the speed of light, and if civilizations are separated by millions or billions of light years, then the silence is simply the sound of signals that have not arrived yet, or that were sent before there was anyone here to receive them, or that passed through this region of space before the Earth formed. The universe could be full of voices, and we could still hear nothing, not because the voices are absent, but because the distances are too large and the timescales too long for any conversation to have occurred yet. But the silence is worth examining more carefully than this, because it is not just the silence of empty radio frequencies. It is the silence of every channel we have learned to listen on. We have surveyed the sky in radio wavelengths systematically for decades, beginning with the earliest organized searches in the 1960s and continuing with increasing sensitivity and coverage to the present day. We have detected no signal that bears the hallmarks of technological origin. We have looked for structured patterns, for narrow band transmissions of the kind that natural processes do not produce, for repeating signals that might indicate deliberate broadcast. We have found interesting anomalies over the years, signals that briefly seem promising before being explained by natural sources or terrestrial interference. But we have found nothing that has held up to scrutiny as evidence of technological intelligence elsewhere. We have also looked beyond radio. We have searched for optical pulses, brief, intense flashes of laser light that a technologically advanced civilization might use to signal across interstellar distances. We have looked for the signatures of large-scale engineering in the infrared, the excess heat that would be produced by a civilization that had built structures around its star to capture its energy output. We have examined the chemical compositions of planetary atmospheres in other solar systems for combinations of gases that could not be maintained by chemistry alone and might indicate biological or technological processes. None of these searches has produced confirmed evidence of anything beyond natural processes. The silence extends further still, into the domain of the cosmic web itself. If any civilization anywhere in the observable universe had developed the capacity for intergalactic travel or intergalactic communication, at a scale large enough to leave detectable traces on the structure of galaxies, we might expect to see evidence of that in our observations of the cosmos. Galaxies that had been deliberately modified, energy signatures that could not be explained by stellar or galactic processes, structures in the distribution of matter that bore the hallmarks of engineering rather than gravity. We see none of these things. The cosmic web looks exactly as the standard model of cosmology predicts it should look based on purely physical processes. Gravity and dark matter and dark energy and the initial conditions of the Big Bang account for everything we observe, with no residual signal that requires intelligence to explain. This comprehensive silence across every channel we have examined is worth sitting with as a fact, not as a conclusion about what it means, but simply as a description of what we have found. The universe is approximately 13.8 billion years old. It contains roughly 2 trillion galaxies, each containing hundreds of billions of stars, many of those stars accompanied by planetary systems, Many of those planetary systems containing planets in the range of temperatures and compositions that allowed life to arise on Earth. The universe has had, by any reasonable estimate, an enormous amount of time and space and raw material in which complexity and life and intelligence could potentially have arisen. And across all of that time and space and all of the channels through which a technological civilization might make itself detectable, we have found silence. The silence does not prove that we are alone. Absence of evidence is not evidence of absence, particularly when the distances involved mean that signals from the vast majority of the universe could not have reached us yet, regardless of when they were sent. The observable universe is 93 billion light-years across, but we have only been capable of receiving radio transmissions for approximately 100 years. The sphere of space from which a signal sent 100 years ago could have reached us by now has a radius of 100 light-years. We have sampled a sphere 100 light-years in radius out of a universe 45 billion light-years in radius. On that basis alone, the silence is entirely expected and tells us essentially nothing about whether we are alone. But the silence does interact in interesting ways with the distances we have been exploring throughout this video, because those distances are not just large. They are, as we have established, in many cases permanently unbridgeable. The 94% of the observable universe that lies beyond the cosmic event horizon is not just difficult to communicate with. It is physically impossible to communicate with in any direction, sending or receiving from this point forward. Whatever civilizations may exist in those galaxies, whatever signals they may have sent or be sending now, are as permanently beyond contact as if they did not exist at all from our perspective. The Fermi question, asked about the universe as a whole, has a partial answer built into the geometry of space. The universe may contain countless voices, but the structure of space ensures that most of them can never reach us, regardless of how long we listen. Within the reachable universe, the 6% that lies within the event horizon, the distances are still enormous. The nearest large galaxy beyond our local group is tens of millions of light-years away. A signal sent today and a reply sent immediately upon receipt would take tens of millions of years for a round trip. Any exchange of information across even the nearest intergalactic distances would unfold on timescales that are long compared to the entire history of human civilization. The silence we currently hear from other galaxies is therefore not surprising, even if those galaxies are full of technological civilizations broadcasting continuously. We have been listening for a few decades with instruments sensitive enough to detect certain kinds of signals at interstellar distances. We have not been listening for anything like the time required for signals from other galaxies to have reached us after our own signals reached them. There is a particular version of the silence that is the most profound and the hardest to resolve, and it is the silence within our own galaxy. The Milky Way is old. It has been forming stars for approximately 10 billion years. In that time, many stellar generations have lived and died. Many planets have had time to form and cool and potentially support the development of life and intelligence. If any civilization in the Milky Way had developed the capacity for interstellar travel, even at a small fraction of the speed of light, and had begun expanding outward from its home system, it could in principle have spread to every star in the galaxy within a few tens of millions of years, a tiny fraction of the galaxy's age. The fact that we see no evidence of this, no evidence that any civilization has ever colonized or significantly modified the Milky Way, is the most direct and locally relevant version of the Fermi paradox. The answers to this version are the same as for the broader question, and they resolve into a few fundamental possibilities. Either life is rare enough that we are among the first technological civilizations in the Milky Way, or civilizations do not tend to expand in the way the colonization argument assumes, or there is something about the development or persistence of technological civilizations that makes them short-lived, or the evidence of other civilizations exists, but we have not yet recognized it. Each of these possibilities has its own implications, and none of them can be ruled out by current evidence. What the distances explored in this video add to this question is a kind of clarifying frame. The universe is not silent because it is small. It is not silent because signals would have little distance to travel. It is silent despite being enormous, despite having had billions of years for signals to propagate, despite containing a number of potential sources of intelligence so large that the number itself resists comprehension. The silence echoes across distances that make the word vast feel inadequate, and it has been echoing for as long as anything in the universe has been capable of producing a signal that could be heard. That silence is not the same as emptiness. The universe is full of matter and energy and structure and process. The stars are burning. The galaxies are turning. The cosmic web is growing more pronounced with every billion years. Somewhere in the 2 trillion galaxies of the observable universe, chemistry is almost certainly doing what chemistry did on the early Earth, building complexity from simple ingredients under the influence of energy and time. Whether that chemistry has anywhere produced the particular kind of complexity that asks questions about the silence is what remains genuinely unknown. The silence, then, is not an answer. It is a condition. The universe presents itself to observation with all of its structure visible and all of its channels open, and nothing but natural processes detectable on any of them. That may be because we are rare. It may be because the distances make detection impossible even in a populated universe. It may be because we have not been listening long enough or in the right ways. It is probably some combination of all of these. But the silence is real, and it sits within the larger silence of the intergalactic voids, and both silences are, in their different ways, among the most significant facts about the universe that careful observation has revealed. Chapter 9. Darkness as Structure. There is a temptation, when thinking about the universe's emptiness, to treat it as an absence, to think of the darkness between galaxies as the background against which the real story of the universe plays out, the featureless stage on which the interesting actors, the stars and galaxies and clusters, perform. That framing is understandable. It is how we naturally think about space in everyday experience, where the interesting things are objects, and the space between them is simply the distance you have to cross to get from one to the next. But it misrepresents the universe in a way that becomes important once you understand the scales involved. The darkness between galaxies is not a backdrop. It is a structure. It is the dominant structure. And understanding it as structure rather than absence changes the picture of the universe in ways that have no clean parallel in ordinary experience. Begin with what the darkness actually contains. The voids of the cosmic web, the enormous regions hundreds of millions of light years across that appear nearly empty of galaxies, are not truly empty in the sense of containing nothing at all. They contain dark matter, distributed at densities far below those found in filaments and clusters, but not zero. They contain the diffuse intergalactic medium, gas so thin that its density is measured in fractions of an atom per cubic meter, but present nonetheless, a faint haze of ionized hydrogen and helium that fills the spaces between galaxies across the entire volume of the observable universe. They contain photons, enormous numbers of them, the cosmic microwave background radiation that fills every point in space equally, the ultraviolet radiation from distant quasars and galaxies that permeates the intergalactic medium and keeps it ionized. The radio waves and X-rays and gamma rays produced by energetic processes everywhere in the universe. The voids are not empty. They are filled with a thin, cold, dim substrate of matter and radiation that is as physically real as the dense cores of galaxies, simply far less concentrated. The intergalactic medium deserves particular attention because it is among the least visible and most pervasive components of the observable universe. It is estimated that the intergalactic medium contains a substantial fraction of the universe's total ordinary matter, possibly more than the matter contained in all the stars and galaxies combined. Most of this matter is in the form of warm and hot intergalactic gas, heated by the ultraviolet radiation from quasars and young galaxies, and by the shock waves produced when gas falls into gravitational potential wells along the cosmic web's filaments. This gas is extremely difficult to detect directly because it is so thin and so hot that it emits only faintly, primarily in the extreme ultraviolet and soft X-ray parts of the spectrum. But it is there, threading the spaces between galaxies with a tenuous web of ionized gas that connects the visible structures to one another in a way that is not apparent from galaxy surveys alone. The darkness also contains dark energy, which is in some sense the most structurally significant component of the universe's emptiness. Dark energy is not matter. It does not cluster. It does not concentrate in galaxies or filaments or anywhere in particular. It is a property of space itself, a constant energy density associated with every cubic meter of space, regardless of what else that cubic meter contains. Its effect is to drive the accelerating expansion of the universe, pushing space apart at an increasing rate, and its influence is felt equally in the densest galaxy clusters and in the most barren voids. Dark energy is, in this sense, the defining property of the emptiness. It is what the emptiness does. It is why the emptiness grows. Understanding dark energy requires sitting with a genuine uncertainty that modern physics has not yet resolved. The existence of dark energy is well established observationally. The acceleration of the universe's expansion was confirmed in the late 1990s through observations of distant supernovae, work that was recognized with the Nobel Prize in Physics in 2011. The amount of dark energy required to explain the observed acceleration is well constrained by multiple independent lines of evidence. But what dark energy actually is, what physical mechanism produces this constant energy density of empty space, remains one of the most significant open questions in all of physics. The simplest mathematical description of dark energy, as a cosmological constant representing an intrinsic energy of the vacuum, fits the data well, but provides no physical explanation for why the vacuum should have the particular energy density it does. A density that is vastly smaller than what quantum field theory would naively predict, and yet not zero. The discrepancy between the predicted and observed values of the vacuum energy density is one of the largest unexplained discrepancies in all of physics, and it sits at the heart of the darkness that fills most of the universe. Dark matter is the other invisible component of the darkness, and unlike dark energy, it does cluster and concentrate. Dark matter halos surround every galaxy and every galaxy cluster, extending far beyond the visible stellar disk of a galaxy into the surrounding space. The filaments of the cosmic web are primarily dark matter filaments, with ordinary matter distributed along them in proportion to the dark matter density. The voids of the cosmic web are not just empty of galaxies. They are comparatively empty of dark matter as well, though not completely so. The distribution of dark matter on large scales follows the same web-like pattern as the galaxies. because the galaxies formed in and around the dark matter concentrations and trace its distribution. But the dark matter distribution extends beyond the visible one, smoothed out over larger scales, filling the spaces between galaxies with a faint, gravitational substrate that influences the motions of everything within its reach. Neither dark matter nor dark energy has been directly detected in the laboratory sense of identifying the particles or fields responsible for their properties. Dark matter's existence is inferred from its gravitational effects, the anomalous rotation curves of galaxies, the gravitational lensing of background light by invisible mass, the large-scale structure of the cosmic web that requires more matter than the visible matter provides to explain its formation. Dark energy's existence is inferred from the accelerating expansion of the universe and confirmed by the geometry of the cosmic microwave background and the large-scale distribution of galaxies. Both are real in the sense of being necessary components of any model that successfully describes the observable universe, but both remain, at the level of fundamental physical explanation, genuinely mysterious. The darkness between galaxies is, in its two most important components, darkness about which physics has much still to learn. There is a proportion worth pausing on. Ordinary matter, the stuff made of protons and neutrons and electrons, the matter of which stars and planets and gas clouds and human beings are composed, accounts for approximately 5% of the total energy content of the observable universe. Dark matter accounts for approximately 27%. Dark energy accounts for approximately 68%. The universe, by its own energy budget, is 95% composed of things whose fundamental nature we do not understand. The visible universe, the part that emits and absorbs light, the part that all of astronomy has always studied, is a thin, luminous skin on a much larger and mostly dark structure. The darkness is not the absence of the universe. It is the substance of the universe. The light is the exception. This proportion has a quality that is difficult to absorb on first encounter and does not become fully comfortable with repetition. We have built an entire civilization, an entire tradition of science and philosophy and art on the basis of observations of a 5% minority of the universe's actual content. Everything we know directly, every star we have named, and every galaxy we have catalogued, and every piece of cosmic structure we have mapped, represents a tiny fraction of what is actually there. The rest is inferred, its existence established beyond reasonable doubt by its gravitational effects and its influence on the expansion of space, but its nature unknown, its composition unmeasured at the particle level, its deeper properties a matter of ongoing investigation and genuine uncertainty. The darkness, understood this way, is not a void waiting to be filled by future discoveries of ordinary matter that we have so far missed. It is a genuinely different kind of content, subject to different physical laws, or at least different aspects of the physical laws we know, interacting with the universe in ways that are gravitational and expansionary, rather than electromagnetic and chemical. The darkness has its own structure, its own dynamics, its own history. It formed the scaffolding on which the visible universe was built. It continues to drive the expansion that is carrying that visible universe toward greater and greater isolation. It is, in the fullest sense, the dominant reality of the cosmos. What does it mean to live inside a universe that is, by its own accounting, mostly dark in this sense? It means that the map we have of the universe is, at best, a map of the shadows cast by the real terrain. The galaxies we observe are traces of the dark matter distribution, useful indicators of where the mass concentrates, but not the mass itself. The expansion we measure is driven by an energy whose nature we do not understand. The voids we identify as empty are full of something we cannot directly see. The entire visible cosmos, rich and complex and beautiful as it is a surface phenomenon, an interface between the ordinary matter and light that we can detect and the vast dark substrate that we cannot. This does not diminish the visible universe. The stars are real. The galaxies are real. The cosmic web in its luminous form is a genuine feature of the universe's structure. But it places the visible universe in a context that changes its apparent significance. The light we see is not the main event. It is a symptom, a consequence, a byproduct of processes operating in a much larger and mostly invisible arena. The darkness is not background. It is foreground, background, and middle ground simultaneously. It is what most of the universe is. The voids, then, are the universe's most honest regions. They are the places where the dark substrate is least obscured by the luminous overlay of ordinary matter. They are the places where the universe most nearly presents itself as it actually is, mostly empty of light, mostly composed of dark matter at low density and dark energy at its characteristic constant value, mostly silent and cold and vast. The filaments and clusters are the exceptions, the regions where ordinary matter has accumulated into dense enough concentrations to ignite nuclear fusion and produce the light that makes them visible across intergalactic distances. Those regions are extraordinary and important, and are where all the complexity we know about lives. But they are not representative. The voids are representative. The darkness is the norm. There is a quality to this understanding that is distinct from the more familiar kind of scientific humility that acknowledges we do not know everything. This is not just a statement about the limits of current knowledge. It is a statement about the structure of the universe itself, a structure in which the knowable, by direct observation, is a small minority, and the dominant reality is accessible only through inference. We live in a universe that hides most of itself, not deliberately, not by any mechanism that resembles concealment, but structurally, as a consequence of what most of it is made of and how that material interacts with light. The darkness is not hiding from us. It simply does not shine. And yet we have found it, not by seeing it, but by measuring its effects, by tracing the curves of galactic rotation and the bending of light around invisible mass and the geometry of the universe's expansion and the patterns of the cosmic web. The darkness has left its fingerprints everywhere in the visible universe, and by reading those fingerprints carefully, we have assembled a picture of what the darkness is and where it is and how much of it there is, even though we have never held a piece of it in a laboratory or seen it emit a single photon. That is one of the more remarkable achievements of the physical sciences, and it rests entirely on the willingness to take seriously what the evidence implies, even when the evidence points towards something that cannot be directly observed. The darkness wins in the end, in the only sense that matters physically. The expansion it drives will eventually carry the luminous universe apart into isolated islands separated by voids so vast that no light can cross them. The stars will burn out. The galaxies will go dark. The last gravitationally bound clusters will become lonely islands in an expanding sea of cold, thin, invisible substrate. The darkness does not act against the light. It has no agenda and no preference. It simply expands, steadily, relentlessly, as it has been doing since dark energy began to dominate the universe's energy budget, approximately 5 billion years ago. And the expansion carries the light farther and farther apart, diluting it, redshifting it, eventually stretching it beyond any possibility of detection. The darkness does not defeat the light. The light simply becomes, over an enormously long time, indistinguishable from the darkness it was always embedded in. That is the structure of the universe. Not a stage with actors on it, but a vast dark ocean with occasional small fires burning on its surface. Each fire a galaxy or a cluster of galaxies, each one temporary on the timescale of the universe's full history. Each one surrounded by distances and silences that the fires themselves can barely illuminate. The darkness is not hostile. It has no opinion about the fires burning inside it. It simply is what it is, the dominant state of the universe, by volume, by mass, by the direction that physics has been trending since the beginning. Chapter 10. What remains? We have traveled a considerable distance in this video. We began with photographs and the specific way they misrepresent the universe, compressing depth into flatness and stacking billions of years of history into a single frame. We moved from there into the distances themselves, the actual separations between galaxies that no analogy built from human experience can quite reach, but that the numbers describe with precision. We looked at the expansion of space, not as a backdrop to the story of the universe, but as one of its central and most consequential features, the mechanism by which the universe is becoming more isolated with every passing era. We examined the cosmic event horizon and the extraordinary fact that 94% of the observable universe is already beyond it, already on the permanent side of a boundary that no signal and no traveler will ever cross. We traced the structure of the cosmic web, the largest organized pattern in the observable universe, built over 14 billion years from the gravitational amplification of quantum fluctuations so small that they existed only at the level of probability. We followed the light record backward to the oldest detectable signal, the cosmic microwave background, and forward to the inevitable fading of that record as the expansion carries the evidence of the universe's history beyond detectability. We spent time in the privileged era, the window in cosmic time when all of that evidence is simultaneously available, and we listened to the silence that answers the question of whether any other intelligence in the universe has made itself known. And we sat with the darkness, not as absence, but as structure, the dominant reality of a universe that is 95% composed of things whose fundamental nature remains genuinely unknown. What remains at the end of all of that is not a conclusion in the sense of a final statement that resolves everything into a clear and comfortable picture. The universe does not resolve into clarity. It resolves into a set of well-established facts surrounded by genuine open questions, and the open questions are not minor details at the edges of an otherwise complete picture. They are central. What is dark matter made of? What produces dark energy? Whether the universe is finite or infinite in extent, whether anything exists beyond the particle horizon, whether life has arisen elsewhere, and if so, where and in what forms, and whether any of it has ever looked at the same sky we look at and asked the same questions. These are not questions that current physics answers. They are questions that current physics has clarified and sharpened and made more precisely askable, but not answered. What remains then is the picture as it currently stands, and the picture, for all its incompleteness, is extraordinary in its scope and in the confidence with which its broad features are known. The universe began approximately 13.8 billion years ago in a state of extraordinary density and temperature. The nature of the very beginning, the first Planck time, the first tiny fraction of the first second, is not accessible to current physics. The mathematics that describes the universe's behavior breaks down at densities and temperatures that high, and there is no observational evidence that reaches back to that moment. But from a fraction of a second onward, the universe's history is described by well-tested physics and the broad outline of what happened is known with genuine confidence. In the first few minutes, nuclear reactions produced the light elements, hydrogen and helium and traces of lithium, in proportions that match precisely what we observe in the oldest and most pristine astronomical objects. In the first 380,000 years, the universe cooled to the point where neutral atoms could form and light could travel freely, releasing the cosmic microwave background that we detect today. In the first few 100 million years, gravity began amplifying the tiny density variations left by the quantum fluctuations of the earliest moments, building the first structures, igniting the first stars, producing the first sources of light in a universe that had been dark since the background radiation faded from visible wavelengths. Over the following billions of years, those structures grew into galaxies and galaxy clusters and the cosmic web, the large-scale architecture of the observable universe, while the expansion of space continued, first decelerating under gravity and then accelerating under the influence of dark energy. The result, after 13.8 billion years, is the universe as it currently is. 2 trillion galaxies distributed across 93 billion light-years of observable space, organized into the filaments and voids of the cosmic web, separated by distances that photographs misrepresent and that analogies struggle to convey, receding from one another at rates that increase with distance, with the most distant already beyond the event horizon and permanently beyond contact, the whole structure embedded in a dark substrate of dark matter and dark energy that accounts for 95% of the universe's total energy content and whose fundamental nature remains one of the central unsolved problems of physics. That is where we are. That is the universe we inhabit. And it is worth spending some time, here near the end, thinking about what it means to inhabit it, not in any mystical or teleological sense, but in the plain physical sense of what is actually happening when something inside this universe turns its attention to the universe itself and begins to measure and describe it. The universe built the conditions for its own observation through a completely unbroken chain of physical causation. The quantum fluctuations of the first second produced the density variations that seeded the cosmic web. The cosmic web produced the conditions for galaxy formation. Galaxy formation produced the conditions for stellar nucleosynthesis, the process by which stars fuse hydrogen and helium into the heavier elements, carbon and oxygen and nitrogen and iron and all the rest, that are necessary for the chemistry of life. Stars that completed their lives and expelled those heavy elements into the interstellar medium-seeded subsequent generations of star formation with enriched material. Those enriched stellar systems produced rocky planets with the chemical complexity necessary for the emergence of self-replicating molecules. Self-replicating molecules, given sufficient time and the continuous pressure of natural selection, acting on variation, produced the biological complexity that eventually gave rise to nervous systems capable of detecting patterns in the environment, and nervous systems, given more time and the accumulation of knowledge across generations, produce minds capable of measuring the expansion rate of the universe, reconstructing the density variations of the plasma that existed 380,000 years after the beginning, and tracing the causal chain that connects those ancient fluctuations to the present moment. There is no step in that chain that requires anything other than physics. No non-physical ingredient is needed at any point. The chain runs from quantum fluctuations to conscious observation through a sequence of well-understood physical and chemical and biological processes, each one following from the previous by the operation of the laws of nature on the materials and conditions produced by those same laws at the previous stage. The observer is made of the same physics as the thing being observed. The measurement is part of the system being measured. The universe, in a specific and local and temporary sense, has produced within itself the conditions for its own description. This does not make us important in any cosmic sense. The universe does not register our presence. The voids do not shrink because we measured them. The expansion does not slow because we detected it. The isolation that is deepening with every passing billion years does not ease because we named it and described it and thought carefully about what it means. The 2 trillion galaxies burning in their gravitational wells have been burning regardless of whether anything within them developed the capacity to look up and ask what they were. The fires do not burn brighter because something in one of them noticed the others, but it does mean something specific about what is actually happening right now in this era, on this planet, in these minds. The universe is, locally and temporarily, aware of itself. Not everywhere, not permanently, not in a way that changes what the universe is or redirects what it is doing. But here, in this fire, in this brief window, when the evidence is still arriving, and the instruments are sensitive enough to read it, and the minds interpreting, the data are connected by language and mathematics into something larger than any individual mind. Something is happening that did not happen in the universe's first billion years, and will not happen in its last trillion. Matter organized in a specific way is comprehending the structure of the whole from inside a small piece of it. The campfire is, in this one instance, aware that it is a campfire, and that the darkness around it extends for billions of light years in every direction. That awareness does not change the darkness. The darkness is vast and it is growing. The expansion continues whether or not anything watches it. The event horizon carries more galaxies beyond contact, whether or not anyone calculates where the boundary is. The cosmic microwave background cools toward its ultimate undetectability, whether or not any instrument is pointed at it. The universe is indifferent, in the complete and literal sense of that word, to whether anything within it develops the capacity for understanding. It does not arrange itself to be understood. It does not simplify itself for the benefit of observers. It simply is what it is, operating according to the laws that have governed it since before the first second, producing whatever complexity those laws allow in whatever regions the conditions permit. And yet the complexity it has produced in this region, in this era, includes something that the universe has not obviously produced anywhere else that we can detect. The capacity for self-reflection. The capacity to ask not just what something is, but what it means that it is. The capacity to sit with a fact about the universe, a fact like the distance between galaxies or the existence of the event horizon, or the silence that answers the Fermi question, and to feel the weight of it, to let it settle, to hold it alongside the other facts and sense the shape of the whole picture that is assembling itself slowly out of a century of careful observation. The distances between galaxies are not just large numbers. They are the measure of the universe's fundamental sparseness, the ratio of matter to space that physics produced from its initial conditions and has been amplifying ever since. The event horizon is not just a boundary on a map. It is the universe telling us, in the language of geometry, that the connection between different parts of itself is not permanent and was never guaranteed. The cosmic web is not just a pretty pattern in galaxy survey data. It is the signature of quantum noise amplified by gravity over 14 billion years, the largest structure in the universe written in the language of the universe's initial conditions. The silence that answers the Fermi question is not just the absence of a signal. It is a fact about the universe's relationship to complexity and intelligence that we do not yet fully understand. All of these things are true simultaneously. They coexist in the universe as we currently understand it, each one connected to the others through the physics that underlies them all, each one a different angle of view on the same fundamental reality. The universe is old and vast and mostly empty and mostly dark and expanding in a direction that leads toward greater isolation and eventual silence. It is also right now, in this era, lit by 2 trillion galaxies organized into a structure of extraordinary beauty and complexity, filled with light that has been traveling for billions of years, carrying information about the universe's full history, and inhabited by at least one kind of mind that has developed the capacity to read that information and assemble it into a picture of the whole. Those 2 things, the vastness and the comprehension, are not in tension. They belong together. The vastness is what the universe is. The comprehension is what the universe has produced in this corner of itself, in this moment of its history, through the operation of the same physics that produced the vastness. The small fire that knows it is a small fire is not diminished by knowing the darkness around it is large. It is, in some sense, that does not require any non-physical explanation, the most interesting thing the universe has managed to do with itself so far. There are things we do not know that are worth naming clearly as we approach the end of this journey. We do not know what dark matter is made of. Multiple candidates have been proposed and searched for without a confirmed detection. The question is genuinely open and may remain open for a considerable time. We do not know what produces dark energy, why the vacuum has the particular energy density it does, or whether that density is truly constant or varies in ways that current observations cannot yet detect. We do not know whether the universe is finite or infinite in extent, whether the space beyond the particle horizon continues indefinitely in the same statistical pattern as the observable universe, or ends in some way, or transitions into something different. We do not know whether life and intelligence have arisen elsewhere, and if so, how commonly, and whether any of it has ever or will ever make itself detectable to anything else. These open questions are not failures of the science. They are the frontier of it. The science has brought us to the point where these questions can be asked with precision, where the terms are defined clearly enough that answers could in principle be recognized if the evidence for them arrived. That is an enormous achievement compared to where the understanding of the universe stood 100 years ago, when the Milky Way was thought to be the entire universe, and the expansion of space had not yet been discovered, and the cosmic microwave background had not yet been predicted, let alone detected. The progress has been real and substantial. The remaining questions are deep and genuine. What we do know, and know well, is the structure of the universe at the level of its large-scale organization. The distances, the emptiness, the expansion, the event horizon, the cosmic web, the light record and its limits, the privileged era and its finite duration, the darkness and its composition, the silence and what it may or may not mean. All of these things are known, not perfectly and not finally, but in their broad features and their causal connections, with a confidence that is grounded in observation and tested against multiple independent lines of evidence. The picture is incomplete. It is also, in its broad outlines, real. The universe is mostly empty. The fires are real. The isolation is structural and it deepens. The evidence of the beginning is being erased by the expansion it produced. The era in which all of this is observable is finite, and we are inside it. None of that is made lighter by understanding it. But understanding it is what we do. It is what this particular arrangement of matter does, in this particular era, on this particular planet, at the edge of this particular galaxy. surrounded by the 2 trillion other fires burning in the dark at distances that photographs misrepresent and that analogies struggle to reach, and that the honest numbers describe with precision. The numbers are correct. The distances are real. The emptiness they measure is the dominant fact of the universe's physical structure. And somewhere inside that structure, in the thin, luminous web of matter that gravity has gathered together against the prevailing trend toward dispersion, something is sitting quietly with all of it, letting it settle in at whatever pace it needs, without being asked to feel any particular way about it, without any conclusions being drawn that the physics does not actually support. Closing. There is a particular quality to the end of a long journey through difficult terrain, not the dramatic quality of arrival, not the relief of having reached a destination, but something quieter and more diffuse, a settling, a sense that the ground covered has changed something about the way the landscape looks, not because the landscape itself has changed, but because you have been inside it long enough to begin to understand its proportions. The distances between galaxies have that quality. You cannot hold them all at once, but after spending enough time with them, moving through them carefully and without hurry, something shifts in the way the darkness above a clear night sky feels. It does not become less vast. It becomes more honestly vast, which is a different thing. We have been moving through that vastness together tonight, and it seems right to spend some time here at the end, not summarizing what we have covered, but simply sitting with it. The facts have been stated. The numbers have been given. The physical mechanisms have been described as carefully as words allow. What remains is not more information, but a different kind of attention, the kind that does not reach for the next fact, but simply rests with the ones already present and lets them mean what they mean. The universe is approximately 13.8 billion years old. In the context of human experience, that number is effectively infinite. The entire recorded history of human civilization occupies less than 10,000 years. The existence of the human species in its anatomically modern form spans perhaps 300,000 years. The existence of life on Earth spans approximately 3.8 billion years, which is itself a number that resists ordinary comprehension. The universe predates life on Earth by more than 10 billion years. Before the Earth existed, before the solar system existed, before the generation of stars that produced the heavy elements from which the Earth is made had lived and died and scattered their enriched material into the interstellar medium, the universe was already old. The expansion had already been underway for billions of years. The cosmic web had already been growing for billions of years. Countless galaxies had already formed and evolved, and in some cases merged with one another. The universe was already, by any measure that matters to human beings, ancient, before any of the chemistry that would eventually produce human beings had even begun. And yet we are here. The chain of causation that leads from the quantum fluctuations of the first second to this moment, this place, this particular arrangement of matter capable of contemplating the distance between galaxies is unbroken. Every link in that chain followed from the previous one through the operation of physical law on physical material. Nothing was added from outside. Nothing in the chain required anything other than physics and time. The universe, through the operation of its own laws on its own contents over its own timescale, produced something that could ask where the universe came from, and how large it is, and what it is made of, and how it will end. That is not a miraculous fact in any supernatural sense, but it is a remarkable fact in a purely physical sense, and it does not become less remarkable through being understood as a physical process rather than a designed one. The 2 trillion galaxies we have been discussing throughout this video are not abstractions. Each one is a physical system of extraordinary complexity, a gravitationally bound collection of hundreds of billions of stars, each star a nuclear furnace converting lighter elements into heavier ones, surrounded in many cases by planetary systems, some of those planets in conditions that allow liquid water, some of those planets in conditions that might allow chemistry to do what chemistry did on the early Earth. We do not know how commonly that chemistry produces life. We do not know how commonly life produces intelligence. We do not know how commonly intelligence produces the capacity for self-reflection and observation. We do not know whether the silence we have discussed is a statement about our rarity or about the distances that make detection impossible, even in a universe full of voices. These are genuinely open questions, and their openness is not comfortable, but it is honest. What we do know is that it happened here. Whatever the probability of its occurrence, whatever the rarity or commonality of the conditions that produced it, the chain of causation ran to completion in this solar system, on this planet, in this era. The capacity for understanding the universe emerged from within the universe, from matter that had been shaped by the universe's full history, into something that could turn its attention back on that history and begin to reconstruct it. That is what has been happening in the centuries of careful astronomical observation that produced the picture we have been exploring tonight. And it is what has been happening in this room, or this bed, or wherever you are as you listen to these words. The universe, in this small corner of itself, is looking at itself. The measurement is part of the system being measured. The observer is built from the same physics as the thing being observed. Let us spend a moment with the specific facts that have settled most heavily over the course of this journey, the ones that seem worth returning to as this night draws toward its end. The fact that photographs flatten depth and time simultaneously, so that what looks like a crowded neighborhood of galaxies is actually a line of sight compressed across billions of light years and billions of years of history, means that the universe we see in images is not the universe as it actually is in three-dimensional space at a single moment. It is a cross-section of history, a temporal archaeology rendered in light, with the oldest material at the back and the most recent at the front. Every time we look at a deep field image, we are not seeing a neighborhood. We are seeing time itself, stacked in depth, the history of the universe preserved in the only medium available for the purpose. Light arrives from every era simultaneously, and what we call the observable universe is really the observable history of the universe, a record that extends back nearly to the beginning, and that is still being written with every photon that arrives at every telescope on every clear night anywhere on Earth. The fact that the expansion of space is carrying galaxies away from us at rates that increase with distance, and that beyond a certain distance the expansion carries them away faster than light can close the gap, means that the universe we can observe is not the same as the universe we can reach. The observable universe is a sphere approximately 93 billion light-years in diameter. The reachable universe, the region from which any physical contact is still possible, is a sphere roughly 32 billion light-years in diameter. The difference between those two spheres, the vast shell of observable but unreachable space, contains the overwhelming majority of what we can see. 94% of the galaxies we can observe are already beyond any possibility of contact. They are present in the light that arrives. They are absent from any possible future in which something physical travels between us and them. The universe shows us things it will not let us touch, and the gap between what is visible and what is reachable is one of the most significant facts about the cosmos that careful physics has revealed. The fact that the cosmic web, the largest organized structure in the observable universe, grew from density variations of roughly 1 part in 100,000 in the early universe means that the intricate architecture of filaments and voids and clusters that we have been describing throughout this video has its ultimate origin in quantum noise. The quantum mechanical uncertainty that produced tiny fluctuations in the density of the early universe was the seed of everything that followed. Those fluctuations, amplified by gravity over 14 billion years, produced the cosmic web. The cosmic web produced the conditions for galaxy formation. Galaxy formation produced the conditions for stellar nucleosynthesis. Stellar nucleosynthesis produced the heavy elements. The heavy elements produced the chemistry. The chemistry produced us. The largest structure in the observable universe and the smallest scales of quantum mechanics are connected by an unbroken chain of physical causation that runs through the entire history of the cosmos. The quantum and the cosmic are not separate domains. They are the beginning and the middle of the same story. The fact that the universe is approximately 95% dark, composed of dark matter and dark energy, whose fundamental nature remains unknown, means that the map we have of the universe is, at best, a map of 5% of its actual content. The visible universe, everything that emits or absorbs light, and is therefore in principle detectable by any electromagnetic instrument, is a thin, luminous skin on a much larger and mostly invisible structure. The stars and galaxies and gas clouds that have always been the subject of astronomy are real and important and beautiful, but they are not the main event. They are a minority component of a universe that is dominated by things we cannot directly see and whose ultimate nature we do not fully understand. The darkness is not a backdrop. It is the substance. The light is the exception. The fact that we are inside the privileged era, the window in cosmic time when all of the evidence needed to reconstruct the universe's history is simultaneously available, means that the knowledge we have built over the past century of astronomical observation is not knowledge that could have been built at any time. It required being here, now, in this era, before the expansion has carried the evidence beyond detectability. An observer in the far future would look out at a universe that appeared to contain only a single large galaxy surrounded by empty space, with no detectable background radiation and no visible neighbors to measure the recession of. They would have no way of knowing that the universe had ever been anything other than that single isolated island. The entire framework of modern cosmology, everything we know about the Big Bang and the cosmic web and the expansion and the event horizon, would be invisible to them, not because the science would be inadequate, but because the evidence would no longer be there. We are fortunate, if fortune is the right word for the accident of our cosmic timing, to be here while the window is still open and the light is still arriving. The fact that the sky is silent, that decades of careful listening on every channel we have learned to use has produced no confirmed signal of technological origin from anywhere beyond our immediate neighborhood, sits alongside the fact that the universe is almost incomprehensibly vast and ancient and full of the raw materials and conditions from which life arose on Earth. Those two facts have not yet been reconciled into a clear picture. The silence may mean that we are rare, or that the distances make detection impossible even in a populated universe, or that technological civilizations are common but short-lived, or some combination of all of these things. The silence does not answer the question of whether we are alone. It leaves it open, which is the most honest place to leave it given what the evidence currently shows. And the fact that we are here at all, that the chain of causation ran to completion in this corner of the universe and produced something capable of asking these questions, is not a fact that the universe arranged on our behalf. The universe did not optimize itself for our benefit. It did not design the physical constants to produce chemistry or biology or intelligence. It operated according to its laws, and its laws in this region, in this era, happen to produce the conditions for all of those things. Whether the laws are fine-tuned in any meaningful sense, whether a different universe with different constants would also produce complexity and intelligence, or whether the specific values we observe are necessary for any of this to arise, is another genuinely open question that current physics has not resolved. What is not open is the simpler fact. The conditions arose, the chain ran, and here we are. Here we are, in this solar system, on this planet, in this thin biosphere, within this civilization, within this room, at this hour, surrounded by a darkness that extends for billions of light years in every direction, filled with 2 trillion galaxies organized into the cosmic web, each galaxy separated from its neighbors by distances that photographs misrepresent and analogies struggle to convey, the whole structure expanding outward under the influence of a dark energy whose nature we do not understand, carrying most of it beyond any possibility of contact, lit by stars that are temporary against the timescale of the universe, producing a light record that is available now and will not always be available, asking questions that are genuine and that some of them do not yet have answers. That is the view from here. Not a comfortable view, in the sense that comfort requires a scale that fits the human body and a time scale that fits the human life, but a true view, as best as careful observation and careful thinking can produce. And there is something in the truth of it that has its own quality. Not comfort exactly, but something that might be called the opposite of loneliness, the sense that the darkness is known, that its dimensions have been measured, that the fires burning in it have been counted, and their distances determined, and their histories traced back to the quantum fluctuations of the first second. The darkness is not unexamined. The fires are not uncounted. The record is not unread. Someone, somewhere in the thin filament, where gravity held enough matter together long enough for biology to arise and biology to produce awareness, looked out at the 2 trillion fires burning in the dark and began carefully, patiently, without urgency, to understand what they were. Tonight has been part of that. Not the dramatic part, not the part where a major discovery is announced or a long-standing mystery is resolved. The quiet part, the part where the known facts are laid out carefully and given enough time and space to settle into something that resembles genuine understanding rather than just a collection of impressive numbers. The universe is large. The distances between galaxies are real. The expansion is ongoing. The horizon is where it is. The darkness is what it is. The silence is what it is. The privileged era is finite, and we are inside it. None of that changes tonight. The galaxies are in the same positions they were when you began listening. The cosmic microwave background is still arriving from every direction, at 2.7 degrees above absolute zero. The Andromeda Galaxy is 2.5 million light-years away, and 2.5 million years closer in transit time than it was when the light now reaching your sky first left its source. The expansion continues at its measured rate. The event horizon sits where the mathematics of space-time places it, at approximately 16 billion light-years, carrying more galaxies beyond it with every passing century in the way that things move in cosmology, slowly, without drama, without a sound. The stars will be in the same positions tomorrow night. The cosmic web will be in the same configuration, grown imperceptibly more pronounced by one more day of gravity doing what gravity does. The faint smudge of Andromeda, will still be visible on a clear dark night to anyone patient enough to let their eyes adjust and look in the right direction in the autumn sky. The light arriving from the most distant observable galaxies will have traveled one more day's worth of distance since tonight, carrying its ancient record one step closer to the instrument that will eventually collect it and add it to the growing inventory of what is known. All of that will be there. The universe will continue to be what it is, doing what it does, at the pace it has always operated at, indifferent in the complete and literal sense to whether anything within it is watching or measuring or understanding. And somewhere inside it, on a small rocky planet in the outer arm of a middling spiral galaxy, in a modest cluster of galaxies in a filament of the cosmic web, something will wake tomorrow and look up at the same darkness and carry with it whatever settled in tonight. The distance between galaxies, the expansion that cannot be reversed, the light that keeps arriving from sources that no longer exist in the form they had when the light left, the silence, the darkness, the fires, and the fact that the fires are counted, that the darkness is measured, that the silence is listened to, that someone in this brief and extraordinary window when the universe is still readable is reading it. Rest well. The universe will be here when you wake. If this was a good companion tonight, a like or a subscribe helps other curious minds find their way here.